problem. Okay. So that this information can help everybody. Say you were trying to type an answer into your homework, and the answer looked something like that's a multiply. And the answer looked something like that. E. Okay, so if you add this number on your calculator, it would probably spit out something like this. Everyone's familiar with this notation, I hope? This is what you can write into WebAssign, and it has a much easier time understanding that than this.
See when I did it?
I used to do that too, frankly.
You know what? Can we just have a homework session today?
I am going to talk about at least one homework question.
Okay,
For the bulk of lecture today, I do need to begin talking about some of Chapter 8. I'm going to take you through everything, all right? I left this nice, handy spreadsheet out for you.
Chapter 8's not mine.
Yes.
Like
Is that more or
More.
side note, for part C on number 11, I keep getting it wrong to the point where it's just like, yeah, you should rework your solution from the beginning and check each step again.
11's the one I'm going to talk about today.
Okay, beautiful.
Oh, good, that's the one.
Are you?
No, I wanted 12.
I thought I talked about 12.
You did, but I went back and it's just way different than, like, the one you did was so much simpler than the one I gave us. Is lab long today? Just so after I can talk to you, like, is it a long one?
No.
So I can talk to you after.
Yes.
Isn't it about the same as last week? A little shorter?
After I worked out all the kinks of the new equipment, people were wrapping up by about 3:30 usually.
That's good.
Yeah.
Okay.
Have you seen Joker yet?
No.
You should watch it.
I've heard it's scary.
And that's why I haven't seen it. That's
Oh, yeah,
why I
it's-
haven't seen it.
it's
I
not-
don't like horror movies.
it's
This
not
is a
scary.
psychological horror movie. What?
Do the Joker.
Don't.
Okay. I
It's
have
not-
a working impression of Mark Hamill Joker, but I'm not doing that now because it involves psychotically laughing, and that's going to echo through the building.
try this?
Not now.
Just
Work on
it
chapter
out.
8.
You show a movie laugh.
Maybe at the end of lecture after I turn the camera off.
There you go.
Fair enough.
The Joker's like, it's not scary, it's just like, you won't walk out of the movie theater feeling good.
I go to the movies to escape real life. I don't want to go and make me feel sad. I'm sad enough already.
Understandable.
So, a lot of things we need to discuss today. And the first big thing hovering over everyone's head is the test that's coming up. To help assuage any issues with the test, I need to remind you all, it's all going to be fine.
You say that every time. Did you see our last test grades?
And the last test was too
Can
hard.
y'all just make it too hard?
Come up with a real scale.
See, last time it was too hard and we all cried, but we all came out okay.
Okay,
We think.
if it was
We're not
like the
sure.
study guide you sent out, then it would have been a good test of our knowledge.
Which is the point.
So are you gonna do that again, send out a study guide?
Yes.
Oh, thank God.
So the test is being finalized. That will help me write good practice questions. I will send those out before the weekend. It just depends on when I can write them. That'll either be today or tomorrow.
That will be similar to the test.
Yes. Similar kinds of questions that involve the same kind of concepts.
Nice.
For a second, I thought you were like asking for money.
I'm okay, thanks.
Now, test is on Tuesday evening, which means that lecture on Tuesday can be dedicated to things like test review and homework questions. Why did I punch my hand? So, Tuesday before the test is review. That means that today we're going to talk about, after we start talking about what's on the test and I give you a little more help on your homework, we're going to spend a little bit of time talking about a little bit of Chapter 8. Because it's just the next step from Chapter 7. It's literally like just an extension of 7. It's not like brand new stuff. It's all related. It's just some extra concepts so that we can keep moving forward. I need to drink water.
Me too.
Will the test be in Coon or white law?
We're hoping white law.
I don't like white law.
Really?
It's a little oppressive.
But you have more surface area to work
That's
with.
true.
That is nice.
Could you paint us a window in there, like on the white
Paint
board?
us a
That'd be nice. Yeah.
I mean, there's a projector. We could put up slides from like Tahiti or something.
That works. I just like really feel like I'm in prison when I go in there.
It's better than that.
I guess, yeah, I'm used to working in physics dungeons, so I'm used to this.
See, I had micro
It's
and
right in here.
organic one after the other class.
Don't this one.
Okay, test is Tuesday. Class Tuesday will review. What will be on the test is as follows. There's going to be a tiny bit of Chapter 4, but frankly, Chapter 4 was going to be there anyway because Chapter 4 was forces, and you need forces to do everything else. So these concepts would have been there anyway. The types of force dedicated questions you might expect to see involve pulley systems and friction, which is again the stuff that you would need to do the rest of it anyway. So just a little bit of Chapter 4. From Chapter 5, that chapter was on work, energy, and power. That's all going to be there. Chapter 6, momentum, impulse, and collisions, both of the two types. That's all going to be there. Chapter 7, the one that we are finishing up. Rotation, angular variables, including angular displacement, angular velocity, and angular acceleration. Centripetal force and centripetal acceleration. And the concept of centrifugal force, but centrifugal force is the one that isn't real. It's a feeling, not a force. This is my kooky shorthand for universal law of gravitation, which is this one. That's the universal law of gravitation. We use that for orbit type questions. Similarly, we use the one formula from Kepler's law for orbit as well. These formulas are on your formula sheet, so you don't need to memorize the formulas, you just need to know what they are and how they can be used. You also have G on your formula sheet. So, this just refers to this formula. This just refers to this formula. The formulas are on your sheet. Just be able to recognize them and be able to do algebra with them.
You said the second one is Kepler's law?
Yes, this is Kepler's third law.
What is M?
Sorry.
What's M?
So if you were trying to find the orbital period for the moon orbiting Earth, the Earth is the thing being orbited, so this would be the mass of Earth. If it was the Earth around the sun, that'd be the mass of the sun. It's always the thing at the center being orbited, the larger mass, which is why it's a big M instead of a small m. And we're going to begin talking about a small amount of Chapter 8 that will be referenced. There will be just a tiny little bit of it involved. It's just more of Chapter 7. So again, it's not like all of a sudden I'm going to ask you a single electricity question. So just more rotation, a couple more additional applications. Just need to move a little farther forwards so we're good by the end of the year. In addition to these, there will be the one retroactive Test 1 bonus question at the end to earn additional points back on the first test. That will help us finalize the first test grade and we will figure out a curve grade system that is fair for everybody. This question, the bonus question will most resemble question 8 from the first test. Yeah, that's 8. In that it will involve the Fantastic Four equations and be about two-dimensional displacement. The original version of the question was just required too many steps to actually be able to be worked in a reasonable amount of time. So
Repeat that, I'm sorry.
the bonus question to give you points on the first test is going to be about two-dimensional displacement, and it will involve Fantastic Four equations. and the same kind of basics that we started with that we've needed the entire semester.
Is it gonna be an acceleration graph again?
Acceleration will be involved. Okay, question 8 from the first test involved an object displacing as it was accelerating at different rates.
Yeah. Is that gonna be the graph in it?
There wasn't a graph involved.
Well, if you drew a graph, that's what it was, an acceleration graph.
I guess you could have drawn a graph. So it could. There was a way to work it without a graph. I worked it without a graph.
Physics is a crack.
But
So physics is on crack.
no, not saying it. Moving on.
How long will this test be? 'Cause that's a lot of material. Like way
There's a
more than
lot of
last
it.
test.
True.
Well, keep in mind, this is tiny bit, and chapter 8 is tiny bit. So that's mostly just 3 chapters. And last time we had about 3.5 chapters.
So like 8 questions.
Granted, it will be longer because this is now attached, but you already have as long as you need to take it.
Did anybody take like the full 5 hours?
I think I left at like 11 p.m.
I was gonna do that just.
There was only like 2 or 3 people here that late.
I gave up before that.
At that point, they were just sort of sitting there waiting to see if they came up with anything better. Okay, so that's what it will be on the test. Again, I will send out practice questions this weekend, and we'll spend Tuesday reviewing, preparing. And then take it at night, take a nap beforehand, eat dinner beforehand, and everything's going to be fine. So, any questions about that before I open up to some homework questions?
Let's do some homework.
Okay, the specific homework question that I have prepared my notes for today is the bat, because this one asks some odd things that I feel need some explanation. This is Batman's pet bat. That would make it Bat. That's what I've been calling this question because I'm crazy. So, this particular kind of bat flies using wings, and everything that flies using wings, the whole point of the wing shape is to turn air resistance into upward lift. So the whole point is that shape, that wind resistance, creates upward lift to counteract the force of gravity. So when you are flying, and when you are level, before you start tilting to turn, when you are level flying, you want force of lift to equal force of gravity. That's what keeps you from falling out of the sky. Now, this particular bat, the exact number is going to change for everyone based on their version of the question, but this problem tells us that the force of lift on the bat is less than or equal to some constant. Everyone's exact constant will be different, but you will know what it is. Some constant times the bat's velocity squared, which means that the force of lift depends on how fast the bat is moving. So, the first question is, what is the minimum speed that the bat can have if it has a specific mass? Everyone's mass is different, but you do know the mass. Now, when the bat is flying level, before it starts trying to turn, when it's just flying forwards in a straight line, theta is 0, it's level. In that scenario, you need lift to be equal and opposite to gravity, or else you start falling. Now, if the bat starts tilting, lift is now at an angle, because lift, it's kind of like normal force. It's perpendicular to the surface creating the lift. So, if the bat tilts a certain degree, lift is now at an angle. That means it has a y piece and an x piece. But the y piece still has to be equal and opposite to gravity, or else the bat falls. So the y piece always has to remain equal and opposite to the force of gravity. But since the hypotenuse is always the longest side, as the angle changes, lift has to change. The total force of lift does. As the bat increases its angle, lift has to get bigger and bigger, which means that lift is at its smallest, and therefore the velocity is at its smallest when the bat is level. So that's the situation you need to look at to determine the minimum speed that the bat needs to stay in the air. So, over here I've listed the starting points for each part of this problem. For part A, you are looking at when the bat is level. When the bat is level, force of gravity would have to equal force of lift. You know mass and you know 9.8, so you can find force of gravity. And the formula for lift is that constant times v squared. If you know m, you know g, and you know that constant, you can solve for v. And that will tell you the minimum speed the bat needs in order to stay in the air. So that's your setup for part A. Part B, you change a little bit. In part B, the bat is now flying at a known velocity, and it is trying to turn. So it is already tilted to some unknown theta. It is moving at a linear speed of 16 meters, well, some amount of meters per second. It is now trying to turn. Now, what is the same in this scenario is the vertical component of lift still has to be equal and opposite to gravity, or else the bat falls. And if the bat falls, it changes what horizontal plane it's on. And so the problem asks, what angle do you need to maintain your horizontal plane? What it really means is, what angle do you need to be at so that the vertical force of lift, the vertical component of lift, is still equal and opposite to gravity, and so you don't fall. It wants to know the angle that you need to be at so that you don't fall. In order to do that, I need to wake my laptop up. And then, the drawing, the vertical forces on the bat are gravity and the vertical component of lift. So now that we've tilted, the vertical component of lift needs to be equal to the force of gravity. You know mass, you know g, you find lift the same way as before, so constant times v squared, and it tells you what v is now. So you can find the new force of lift at this new faster velocity. The only thing left then is to find the theta that allows this to work. So moving at this velocity, you need to tilt to a certain angle so that these two things are equal to each other. If you're not at that angle, then you won't fly as expected. And this is why pilots have very tough jobs. They have to do all this on the fly. Crap, that's a pun. I realized it before I said it, but I'd already started the joke. Okay. The last part is actually the most straightforward because it just uses our normal formulas. In part B, you're given a velocity and you find theta. You need to keep those two numbers for use in part C. In part C, it asks the radius of the bat's turning as it's flying at the speed listed in part B, which means it's also tilted at the same angle that you found in part B. So do part B first, get your correct answer first, because you need it in part C. Now, the horizontal component of lift is going to act as the centripetal force. And so that force is always going to point towards some fictional point at the center of the circle as the bat turns and circles around that point. So you're solving for the radius from the bat to that point, the radius of its turn. The x component of lift at this angle is the centripetal force. So your starting point that I've got over here Centripetal force is equal to the horizontal component of lift, and that's equal to mass times velocity squared over r. This is just mass times centripetal acceleration. And what you're solving for here is the radius. So for all three parts, these are your starting points. This question just asks for things in a very odd way, so I wanted to help everyone through the setup. Where are my erasers? So does anyone have any questions about this question? Or any other questions in general?
So everything we do on this question, we're gonna use the. When we're doing B, we can use everything from A to get B.
No. Well, okay. This, yes. This is that's mass. That stays constant. A is asking for the minimum speed. You won't use this answer anywhere else. After part A, you are told this is the maximum speed and the bat stays at this. So this remains. This you only find once. Okay. Does bat make more sense now? Okay. Any other questions before I move on to just the tiniest bit of chapter 8 that we move forward? Okay. So, as I was saying, this next chapter is just more rotational motion. We're just covering the basics of it now, so we can keep moving forwards towards the end of next week. And just because there's going to be a tiny, tiny bit of this on the test. Now, it's the theme from last chapter is that everything that exists linearly has an angular counterpart. And I do mean everything. Everything that has a linear variable has an angular counterpart. So linearly, we have displacement, velocity, and acceleration. Angularly, we have angular displacement, angular velocity, and angular acceleration. Those are the three we've talked about so far. The angular linear worlds are like, again, parallel sci-fi counterparts to each other. This is the normal universe. This is the evil mirror universe where everyone has a mustache for some reason. And everything from the original universe has a counterpart over here. So we're going to talk about a few more of those counterparts. So those are our linear formulas. I'm showing you all of these now. We're not going to get through all of these today. We're only going to talk about the first couple today. Linearly, we have Newton's second law, force equals mass times acceleration. We have, my apologies, I should have changed this. This is little rho momentum, not big P power. Little rho momentum. Momentum equals mass times velocity. Force, change in force equals momentum rho over time. Power equals force times velocity. And this is kinetic energy. And all of these also have angular counterparts. The formulas take exactly the same shape. You just replace them with the angular versions of what was there originally. Like I said, we're only going to talk about the first couple today. We're not going to get through this entire list. The entire list is not going to be on the test. I'm just showing it to you now. It's on your formula sheet, but just showing it to you to start with. So every single one of these lines up with its counterpart directly across. Notice, they're all still the same shape. I'm just going to take this down real quick. I just need to check my notes for a moment. Okay, and it's back. So does everyone have these? Okay, I'll just say a few words real quick. The thing that we're going to spend the most time on today is this first one. This is the angular counterpart to Newton's second law. And so this would be angular force equals angular mass times angular acceleration. That said, these have names other than those things. Very specifically, every I that you see over here, that's called moment of inertia. And that's the angular counterpart to mass. Projector seems like it's twitching today. The hologram is moving. Okay, so we're going to begin with this one. This here is the angular counterpart to force, and it's called torque. I'm going to put a slightly different formula up on the board. This is the angular version of Newton's second law. Linearly, linear force, sum of the linear forces equals mass times acceleration. Angularly, angular force, torque, equals angular angular mass, moment of inertia, times angular acceleration. That is alpha, that's not regular A, that is alpha. I'm going to put a different formula on the board real quick. The formula you're about to see is the conversion factor between torque and force. So before, we had things like D equals R times theta, V equals R times omega, and then A equals R times alpha. So our new pair of counterparts is force is the linear version. Its mirror universe twin is, nope, I don't know why I wrote that, is torque. And I've been using a lot of T's lately, so I'm going to help distinguish between all of them. This is a lowercase t, lowercase English t, and that's time. When I use an uppercase T, that's usually tension. Uppercase tau is period of revolution. And this is lowercase tau. And that is torque. Now, are the differences clear enough in my handwriting? Okay. So when I write lowercase tau, it's got a squiggle for the top and then a curved T at the bottom. It's kind of like a backwards J, only smaller. I try to make it visually distinct from regular lowercase t. So this is torque. And torque is something that I know you've all used today, because I know you've all opened at least one door today. You haven't opened the door? Or are you just able to do this and it just opens? I'm not the only one who will walk up to like Walmart or a store with the automated doors and just, as it opens. I can't be the only person who does that.
Maybe the only person in this room, but I promise you somewhere in the world someone else is doing it with you.
Okay. I know I'm a doofus. I just need everyone else to admit they are too. So, this statement right here is the conversion between torque and force. Like how before we had all of the conversions between the linear and the angular counterparts. So, torque equals radius times force. Now, the application of torque. I mentioned opening doors. If I am standing here at the door, I exert a force on the door to make it move. I exert a force on the mass of the door, it begins accelerating. Straightforward. The thing is, though, that door doesn't accelerate forwards in a straight line. It starts rotating because one end of it is fixed upon an axis of rotation. So when I exert the linear force this way, that force is perpendicular to the lever arm that is the door. And so the force I exert at a radius from the pivot point of the door creates a torque that makes the door spin. And that's just how any door on hinges works. As long as one side of it is a pivot that it can oscillate about, and it's not a sliding door that just goes back and forth. Every time you ever open a door is an application of torque. So, a force perpendicular to the axis of rotation creates a torque, and a torque causes an object to begin angularly accelerating. If you'll recall from the previous slide, torque equals moment of inertia times angular acceleration, just like how regular force equals mass times linear acceleration. If you exert a linear force on a mass, it accelerates. If you exert a torque on an object that can rotate, it will begin angularly accelerating. I will explain what I means in a moment.
What did it say I was in the middle of your...
Well, it's called moment of inertia. I'll put that one back up for a moment. It's called moment of inertia, and it is treated as the angular counterpart to mass. And go ahead and put that one on the chart. So linearly we have mass, angularly we have moment of inertia. They are counterparts to each other in the formula, which is why in the angular version we replace them with I. If the object has mass and can rotate, and you exert a torque on it, it will begin rotating, angularly accelerating. So when I push on the door, it accelerates and starts moving. Same basic concept, just angular instead of linear. And again, you've been doing it your entire life. Some other places where you commonly see torque. The whole point of a wrench is so that you don't have to just take your hand, grab the bolt, and just try to twist it yourself. When you use a wrench, you're still exerting a force. If I was to grab the bolt and just try to turn it with my hand, I'm still exerting a force either way. The difference is, with just my hand, the radius between the force I apply and the pivot point of the bolt is super tiny. If you look at the formula for torque, if radius is tiny, torque is tiny. If radius is a super small number, then torque is a super small number. So if anyone's ever tried to loosen a very tough bolt with your bare hands, it's not easy because you don't have a whole lot of leverage because you're not gripping it from very far away. The radius of the rotation is super small, which means that you are not delivering as much torque. no matter how much force you're applying. The point of a wrench, I can still exert the same amount of force, but now I'm doing it from some radius away from the bolt. I have increased the radius of rotation. So the same force at a greater radius exerts more torque. And that's the entire reason this thing exists. Based on that explanation, can you guys think of any other places where torque is commonly utilized?
Ours.
Okay, you do hear about torque in car commercials, because some ads will tell you about, I haven't even watched car commercials in a while, but I know they've said the word torque before. In a car specifically, the way that that works is, I need more board. So this is a poorly drawn car tire. So that's the rubber end of the tire. On the inside of the tire, there's the axle that is providing a force to make the tire spin. The axle is exerting some force at a radius from the tire's center of rotation. And so, because the tire is spinning, you are exerting a torque to make it angularly accelerate. So, that is why torque is important for a car. You need to use torque to make something spin. And it does this for every single wheel that is powered by the car. There are some other places, though, that torque comes up. Can anyone think of any of them? Okay.
I think you're gonna say something in space, but
We're sorry, we just.
No, that's fine. Spaceships don't use, well, there is one application of torque that would be really cool if we could make it work in space. Has anyone watched The Martian, the movie with Dat Damon in it? All right. In that movie, the ship that the crew leaves Mars in, it sort of looks like a satellite with a big spinny disc on it. That disc is spinning because it's basically simulating gravity. You're inside the disc, and the disc is rotating. The disc exerts a centripetal force on you to keep you in the disc, and that combined with the perception of centrifugal force pushing you out of the disc, or at least that makes it feel like you're being pushed out of the disc, replicates gravity, which is why there were scenes of the returning crew in The Martian actually standing up and walking around the ship and like running on a treadmill. That spinning disc was a way to artificially replicate gravity, which is important if you're going to be on a ship for upwards of a couple of years. Yes?
Well, it's the same, like I mentioned this before, but it's the same way that like pilots in training test for like G-force capabilities, isn't it? And then I know that in Disney World in Florida, there's these like two versions of Arrives. There's one that's more intense, one that's like mild intense. I don't think it goes for more than like 2 Gs, but it's supposed to simulate like a flight like that. You sit in it and it spins.
Right. At a certain number of Gs, blood rushes out of your brain and you pass out. But see, the G, what you're talking about there is angular acceleration, less so than torque. But specifically on a carnival ride where there is a mechanical arm swinging you around, that would be torque because the arm exerts a force on the passenger at a radius from the center. So you do see it a lot in fair rides, yes. I know some of you are hopefully going to understand this one. Baseball. Okay, any sport that uses a bat or a bat-like object.
There was a softball bat called court because the bottom part missed it.
It was terrible.
Yeah, it was horrible, but it was literally called court.
Yes, so the reason that baseball, softball, cricket as sports exist is because it's a lot better to hit a ball with the bat because you're exerting the force at a radius away from your hands. than it would be to just, try to punch the ball in midair.
Yeah, you would break
Grab
your hand.
Exactly. You would A, break your hand, and B, there's no radius there. You're just applying the force directly to your bare knuckles. You're not getting the benefit of having a torque from some other radius away. Also, the bat takes it. You don't. But baseball is the athleticized version of torque. You are using torque to accomplish sports ball.
Hockey, torque as well, right?
Correct. Any activity or sport or repair function that involves using a long tool and rotating it about some fixed axis utilizes torque. So hockey, golf, you're swinging it usually vertically. There's also crowbars. The entire point of a crowbar is to jam one end into like the sewer opening, and then you apply a force at a radius from the lid to create a torque, because that helps the lid rotate, which is a lot easier than just lifting it straight up. Okay, that's a mallet, so yes. Hammers, wrenches, bats, crowbars, any long tool that is designed to deliver a force away from your hands utilizes torque. Alright? Yes. Yes. The longer the sword is, the more torque you get than if you just, was holding the knife between your fingers. Wolverine does not get a whole lot of torque with his knuckle claws, admittedly, but his whole thing is they're adamantium and they'll cut through anything regardless. Okay, so torque exists in your day-to-day life. It is a thing you interact with a lot. Even if you don't sports ball, you do open doors. I don't sports ball, so I'm just a loon. Okay, now, important caveat. Everyone sees the perpendicular symbol there? Yes, this is the perpendicular symbol. This means that the radius and the force applied need to be perpendicular to each other. If I had this wrench affixed to a bolt, would I get any torque if I was pulling the wrench out from the bolt in this axis? No, that wouldn't be spinning, I'd just be taking the wrench off. Because that force would be parallel to the axis of rotation. I only get torque if I push the wrench either down or up, because those are perpendicular to the axis of rotation. So I only get torque if I actually make the wrench rotate. I only do that with a perpendicular force. Same as this door. Is this going to accomplish anything?
Probably
Might
not.
break the door. Or yourself.
So if I'm pulling this way for no clear reason, I don't know why anyone would. If you pull this way on the door that's parallel to the axis, you get no torque, the door doesn't move. If I exert a force this way, perpendicular to the axis, it starts accelerating.
I mean, you could just take out the door by pulling like parallel.
Yeah, but if I Kool-Aid man this thing, I have to pay for it. One other detail. So the radius and the force have to be perpendicular to each other, which means I do need to put this symbol up here. The last thing is, because radius and force are multiplied together, if either number increases, torque increases. If you exert more force, you get more torque. But if you have the same force at a bigger radius, you also get more torque. Conversely, that means if you reduce your radius, torque gets smaller, which is why we put the doorknob as far away from the hinges as possible. The doorknob being on the far end of the door increases the radius to as much as it can be, which increases torque to as much as it can be. But if I'm insane and I decide to push on the door super close to the hinges, it takes a lot more effort. Has anyone ever done this?
Every day.
Cool.
What?
It takes a lot more force to make the door move if I'm pushing here than it does if I'm pushing here. Because the radius is smaller. Smaller radius, less torque. Which is why longer wrenches make it easier to remove bolts. That's why tougher jobs have really huge wrenches.
It's like the tire iron on your car.
Exactly. The longer the tire iron is, the easier it is to remove the bolts. It's just you have to carry around the giant tire iron. Okay, application of this. We're looking at wrenches now. Our wrench is 1 foot long, so we're using imperial units here. Sorry. Our wrench is 1 foot long. We are applying a force of 50 pounds. I suppose it's worth talking about the units of torque while we're up here. Okay, so torque, the variable is tau, but it is measured in newtons times meters, because you are literally multiplying newtons times meters. That's the metric unit of torque.
Can we just change this example to be in metric? Why is it not?
Yeah.
Just for practice.
Give me a second.
I mean, it doesn't, you can literally just change
We
12
just do 1 to 1.
newtons and 12 to something else, or 1 foot to 1 meter.
Yes, just 1 second. A commonly used imperial unit for torque is foot-pounds. Foot-pounds. Has anyone heard of foot-pounds? Okay, not the only one. It does exist. It's literally just, feet multiplied by pounds. But, this is the metric version. So, if you guys find in favor of this, this can be newtons, and we'll change 12 inches to 1 meter. Is that fair?
That's a really big wrench, but yeah.
Yes, it is. Well, pipe wrenches get about that large.
A meter?
Yes, my pipe wrench is about that large, correct? I believe.
Yeah, they exist. That's the kind of wrench you might use to pry open a fire hydrant, probably.
Which is on the meters.
Yes. They exist.
Why do you
I
need that much?
I have one at home that's about half a meter. I know they come bigger than that. Okay, so 12 newtons, 1 meter long. So how much torque do we have? All right. First instinct would be to multiply force by radius. That would give you 12 newton meters. The problem is, the person who is using this wrench doesn't physics good. If the force was 12 newtons this way, perpendicular to the axis of rotation, if the force was this way, then all 12 newtons would be perpendicular and you get 12 newton meters worth of torque. But, sometimes when you're pulling a wrench, you're going to grab and pull towards yourself. Just because that's how arms work, and your first instinct is usually to do something like this if the wrench is big and is away from you. So in this scenario, the force applied is not entirely perpendicular to the wrench. We need to find how much of it is perpendicular. So we've got to use a tiny bit of trig, very small bit, tiny bit. I'll use a different marker. So, force is 12 newtons. We are at an angle of 50 degrees. So there's some x component and some y component. Which leg do we want?
Is our radius?
Yes. So that's the radius of the wrench. That will be our 1 meter. which leg of that force triangle do we want to find force perpendicular to the axis? Yes, the y. This one, the y-axis, our y-axis in this question is the one that is perpendicular to the horizontal axis of rotation. So this is the force that we want to be able to move on. So our hypotenuse is 12, our theta is 50. Which trig function will help us get here?
Sine.
Sine of 50 is going to be our Fy over 12. So Fy equals 12 times sine 50. Make sure your calculator is in degrees if you're plugging in degrees. And that gives me 9.19 newtons. To find our torque, torque is radius perpendicular times force. So that's going to be our 1 meter times our 9.19 perpendicular force, which will give us 9.19 Newton meters of torque. Any questions so far?
So you always use the force that doesn't follow one already?
Correct, because again, this force here is pointing into the bolt. And so if I was just grabbing this wrench and trying to shove the wrench into the bolt, would that make the bolt spin? No.
Probably not.
Only if I apply a perpendicular force to the surface of the wrench is that actually going to make anything start rotating. Again, like if I'm pulling outwards on the door, that accomplishes nothing. I really tricked on my cables. Okay, any questions about torque so far?
So this is an easy example.
Yes.
I mean, what is our test?
This.
That was so
You said
You're gonna
this.
switch it all around.
It depends on how much it depends on how much every section gets through.
When will we know?
Can you
I
just
don't know
put this
about
exact
that.
problem, just switch up the numbers a bit on our test?
Well, look, the test questions that involve this are going to be regular rotation questions, and we will probably ask you conceptually about torque and moment of inertia in the problems you are already doing.
So no math, just
There's a little math. It's physics, there's always a little math.
A little maybe?
Try to get
We
out.
learned a little bit, we probably didn't need it.
Not quite.
Please go
I got
home.
15 minutes more of your time, and I need to get through this today so that we can review on Tuesday.
Oh yeah, we have class.
Yes, but we're not going to learn anything new. It's going to be review for the test you're taking tonight.
Kinda makes me sad.
I won't continue forwards in chapter 8. How about that? You can still learn something. You'll learn how to do the test. I don't know what to make of that look. It's okay. All right. I want to make sure everyone can conceptually wrap their head around moment of inertia today, because moment of inertia shows up in this formula for torque. So I've been saying that moment of inertia is the angular counterpart to mass. Now that's kind of a weird thing to say, because an object with mass is going to have that same amount of mass regardless of how it's moving. It still has the same mass. That's not changing. That's not going anywhere. So the fact that mass has an angular counterpart is kind of strange. Gesundheit. The reason that we need to bother distinguishing between normal mass and angular mass, moment of inertia, is due to the fact that objects tend to rotate differently depending on how the mass of the object is configured. So, I have a few different objects up here with me today. What do these two things have in common?
They're a pole.
Alright, they are metal poles, but there is at least one difference. I'm just pointing them towards you so you can see the difference.
One is hollow, one is not.
One is hollow and one is not. Even if these two objects had the same radius and the same mass, they have different mass distributions. So in the tube, all of the mass is away from the center. It's just a ring around the center. There's no actual material in the center of the object. This, however, is solid. There is actually mass at the center of this tube. Well, that depends, actually. This one over this one, yes, because this one has more mass. But if, hypothetically, they were the same length, the same radius, and the same mass, the only difference being one of them was hollow, but they still had the same mass, how do you think that would change the force of impact between either one of these?
I would feel like if, like, that would hit you, like, it would hit you, but, like, it would distribute force throughout it, type thing, because it would hit you. I don't know how to explain it. Like,
Oh, it's okay. You're wording out your instincts.
yeah, I see it in my mind, but I can't explain it.
That's kind of been my whole thing this whole year. You guys have been seeing this physics your whole life, and you have the instinct, you just haven't put words to it yet. And the words is what I'm trying to help you guys, is the point of the class. Now, because these objects have different mass distributions, even if they have the same mass, they are going to rotate differently. They're going to have different tendencies to rotate about different axes. And the reason we have moment of inertia is to differentiate between the rotational tendencies of separate objects. Because even if they have the same mass, they will have different rotational tendencies depending on their mass distribution, their size, and how they're rotating. Another visual example, I'm hoping everyone will be able to see this. Okay. Say we have this particular object. It can be any object that is rather box-like in nature. It has a length, a width, and a depth. It is a standard three-dimensional rectangular object. Now, the mass of this system is not going to change. But what I am going to change for you guys is I'm going to change the axis of rotation. So this particular object, because it's a 3D shape, can rotate between 3 different axes. I can rotate it lengthwise like this. I can rotate it about this center axis. And I can rotate it about this axis. One through each surface. Now when I'm spinning it in my hands, there doesn't seem to be a whole lot of difference, but I can go ahead and guarantee you it spins a lot easier this way. It doesn't take me as much effort to make it spin about this axis as it does to make it spin about this axis. It rotates a lot more if I just push it the same amount each time. That's because the orientation of the mass affects how it rotates, which is why we need to distinguish with moment of inertia. So, I hope this is going to be easy to see. I'm going to throw it in the air about each of those 3 axes. And I want you to tell me what you see. First, I'm going to do it like this. Now, when I threw this one, it kept rotating about that one axis the entire time. Now I'm going to throw it about this axis. Alright? So it did the same thing. It was still just rotating about the one axis I threw it around. But now I'm going to throw it about this axis. So watch if it actually spins like this. Okay, it's a little hard to tell if I do it fast. So let's see if I can slow it down a little. Alright, watch carefully. It did a backflip. It changed axes in midair. Anyone see it?
Wait, what am I looking for?
Okay.
Is
So-
it like you can't throw your phone up in the air? You have that like.
Oh,
Anyone see that?
do it again.
Yeah.
Okay.
Why?
That's because the distribution of the mass and how it's rotating affect all of this, and all of that is summed up in moment of inertia. Yeah, if you don't mind doing it with your phone again, it's easier to see on the phone. Thank you. So, the mass of the object, the shape of the object, and the axis through which the object is rotating all affect all of these things. And so that all that information is summed up inside the moment of inertia variable. Now, because every object is different, there are a bunch of different moment of inertia formulas. You don't have to memorize any of them. They will be given to you if you need them. This is one of them. This is used for a multi-object system. And so for a system comprised of multiple objects, I'll show you an example of that in a minute. The moment of inertia is the sum of all the individual masses times their radius from the axis of rotation squared. It's a very specific mathematical equal sign, and I shamefully cannot remember what at the moment. I severely apologize for that. Now, to apply this is a multi-object system. These are 4 separate objects that are all stuck together. And the way that you rotate this combined object affects how it will rotate. In this particular sample, the object is going to rotate about this axis through these objects. So that would be like if I grabbed hold of this rectangle and made it spin about its side. So each of the 4 objects has a mass of m, and each of the 4 objects is in a specific place on this particular object. Now, I forgot this was actually an eraser for a second. Actually, wait, I'll just put the thing up and draw on there. So, all of these have a mass of m. But they're all a different radius away from the axis of rotation. How far is this object from the axis of rotation? 0. It's right on top of it. Which means its mass isn't affecting the rotation of the system in this way. So if we do sum of all the m's and r's squareds, we have this m times its radius of 0. This m is also right on top of it, so its radius is 0. This mass is 2a away, so m times 2a squared. And this one is 2a away from that object. So m times 2a squared. This term falls out, that term falls out. So that's going to be 4a squared m plus 4a squared m, which will give us 8a squared m. Is that a question?
Yeah. Why is it 0 again for those?
Because the radius between this mass's center and the axis of rotation is 0. This object is 2a away from this one, it's 2b away from this one, but it's right on top of the axis, which means that in this configuration, it's not contributing anything to the rotation of the system. Because the radius goes away, its mass sort of cancels on this axis and doesn't contribute. But the system would change if I instead decided to make it rotate about that axis. Now this mass and this mass have a radius of 0 and they cancel. And these masses are both 2b away. So that would change the moment of inertia for the system from 8a squared m to 8b squared m. How you made it spin affect the axis through which you're making it spin affects its moment of inertia. And since moment of inertia is the angular counterpart to mass, and mass linearly is a measure of linear inertia, which affects an object's tendency to want to move or to change its movement, the higher the moment of inertia is, the harder it is to change something's movement. Like how normally, the higher mass is, the harder it is to change something's movement. That means if a certain configuration lowers something's moment of inertia, it is easier to make it rotate about that axis. Like how smaller masses are easier to accelerate linearly. And looking at this drawing, A is smaller than B, looking at the drawing. That means about this axis, the moment of inertia would be 8b squared m. If b is bigger than a, that would increase the moment of inertia if I was using this axis. That means it will be harder to rotate the object around this axis than around this axis. It's going to take more torque. It's going to take more effort on behalf of the person who is trying to make it spin. I know we're running out of time, but I have just one quick practical thing I want to show you all. First, this is a chart that shows some of the different ways to find the moment of inertia, and it just depends on the shape of the object. You will be given a chart like this. You don't have to memorize a single one of these because I haven't. These will be presented to you. I just want to show you the formulas to make a point about this tube, this pole. So up on this screen right now, there are 3 different drawings that represent 3 different ways I could be rotating this one pole. This represents a solid cylinder or disc that is rotating about its own lengthwise axis. So that would be if I was doing this. Everyone see that? All right. This represents a long cylinder or tube that isn't hollow, rotating laterally around its middle point. So that would be if I was doing this. It's not anything. And the last one there in the bottom right represents if I was doing this, if it was spinning about one of its end points. I don't have the finger strength to make it do that. The reason I want to show you all of these, and I actually want someone to come up and hold this. Can I get a volunteer?
Kyle wants to do it. Yeah, Kyle.
Yeah, dude.
Okay. Now, looking at the formulas here, The smaller the moment of inertia, the easier it is to make it move. The formula for moment of inertia through this axis is 1/2 m times radius squared. The formula here is 1/12 mass times length squared. The formula here is 1/3 mass times length squared. So based on the formulas, which of these methods do you think is the easiest to make this thing rotate? Requires the least effort. Which one?
The first one.
The first one? Why do you think that?
Never mind.
Okay. Can you replicate all the different methods I was just using and tell me what's easiest? All right, is that pretty easy? Okay.
Helicopter now?
Helicopter, all right.
Don't drop it.
Please don't drop it. All right.
No, I'm just.
Pendulum.
Yeah.
Swing it back and forth. Okay. Of the three, which takes the most effort?
Probably this one.
It's definitely that one. You can try if you want and try to get it to go all the way around.
I'll let it
You let it go?
go. Yeah.
So this takes the most effort. Notice, if you compare these two directly, this one's always going to be smaller because you're dividing by 12 instead of 3. The object wants to spin like this more than it wants to spin like this. So it takes more force and more torque to make it do that. What was easiest?
I don't know. Probably the helicopter.
Really?
I don't know.
It's okay, it's okay. For that tube, this is going to be easiest because even though you're only dividing by 2 instead of by 12, the radius of the tube is a lot shorter than the length of the tube. So it just depends on the object. All this to say, moment of inertia is strange. You will have these intervals, but it's the angular counterpart to mass, and it appears in this formula. Sorry to keep you all over. This class will be Tuesday, where we will review for the test. We'll also send out practice questions this weekend. I hope you all have a wonderful weekend.
Is it chapter
Hope to
8?
see you soon.
Is question gonna be on what else?
This is all of chapter 8 that's going to be there.
I know, but is there gonna be a
The lost
practice
Potter, right?
problem?
Say again?
Is there gonna be a practice problem with the study guide thing?
Yes, it will be based on whatever information about torque and moment of inertia is on the test. Okay?
I don't even know what I'm supposed to use that for.
Realistically, since we've barely done anything with this, you might have to find torque, because that's force times radius. You might already know angular acceleration from a previous part of the question, and we might ask you to find moment of inertia using this formula. We haven't done a lot with it, I realize that. We're not gonna expect you to have this memorized by Tuesday.
I gave you that.
Yes, the office is like the main school office, is it that way? It's really bad at answering my emails, because I'm still waiting to get back my insurance information. But I will try to have something more definitive by the start of next week, I do apologize. Alright,
So will I be able to go to the Thursday lab every week?
I mean, if you can't make the Friday, then yeah, we have to, but yes, so I will tell you, we will let you come to the Thursday lab. It's, what the issue is just us figuring out the best thing to do about the lab in general.
Yeah.
I will tell you, you will be able to attend a lab that you won't miss every week. I'm telling you that. Don't worry.
Okay.
Okay.
I'm think I'm still waitlisted for the other one.
Good. The weird thing is, just because everyone wants the Thursday one, that one's currently filled at like 18, 19.
Yeah.
Friday's at like 5.
Make sure if you
So we
don't feel
might,
like you register.
the department is trying to think of a solution, and that might just involve moving the Friday lab to like Monday.
And then I didn't get it last time.
I have a bio lab Monday, so I mean,
So that
We
wouldn't
had-
help you at all.
Yeah, we had midweek games Tuesdays and Wednesdays as well, so I mean, it's,
Well, it might shuffle some of the people out of the Thursday one if they can make Monday.
yeah.
So I am telling you, we will guarantee that you can attend a lab that you won't miss it.
Alright. So
We
I'm
just
good.
need to figure out, the department needs to decide the best way to make sure that happens. But you will definitely get it.
Sounds good.
Yes. I'll be right over. You can say that with the keys. Right there. Hello, everyone. You guys have questions or, okay.
I'm so tired.
Hello, so tired, I'm teacher. And how are you, Kara? What's your question?
How are you supposed to get cosine by itself in that second equation? I'm struggling with just the algebra of it.
Ah, sure.
Oh, it's your pencil?
Oh, it is, isn't it?